So when we last spoke, we had worked on chapter 8. We'd gotten up through example 8.5, which was a conceptual example. And today I'm going to try to go ahead and finish out chapter 8. I'm not necessarily going to do all the examples. There's, good examples in there and they're worthwhile being done. I'm going to do most of them. And then I'm going to try to jump into chapter 9 so we can get a little bit more caught up. So we will be doing some of chapter 9 today as well as chapter 8. And chapter 9 is on conservation of linear momentum, or specifically linear momentum. So let's go ahead and get started by sharing my computer screen or my iPad screen. Okay, should come up any second now. There we go. So we're starting off with example 8.6, and example 8.6 says estimate pole vault. Estimate the kinetic energy and the speed required for a 70 kilogram pole vaulter to just pass over a bar 5.0 meters high, assume the vaulter's center of mass is initially at 0.90 meters off the ground and reaches its maximum height at the level of the bar itself. So that's a typical problem where we're basically trying to say, okay, we're going to try to convert kinetic energy into potential energy to actually perform a pole vault. So to do this, let's go ahead and take the solution I've got and started off with by writing down my conservation of energy equation that I use. We're going to, in this case, say that we have a kinetic energy and a potential energy initially because I'm going to treat as I wrote right here, I'm going to treat the y equals 0 as u equals 0. And with that in mind, since our center of mass at takeoff is 0.90 meters, then we have a potential energy m times g times 0.90 meters. And of course, she has some initial speed, and therefore her kinetic energy is 1 half mv initial squared. And that's what we're actually trying to solve for. We're not going to worry about any kind of work she puts into it, but obviously that's a real thing. But we are going to try to figure out basically what the max height is, which will be mg times the height. We'll actually not figure out what the height is, but use the height. The final kinetic energy we're going to assume to be 0 because she's going to ideally reach that peak height and then be moving horizontally left and right 0 miles per hour. So we're going to say that final kinetic energy is 0. We're going to say there's no work out because she's not excuse me, not compressing any springs or anything like that, and there's no E loss because we're ignoring air resistance and stuff of that sort. So now I can go ahead and write down exactly what we know. We have mgy is the potential energy, so we'll have 70.0 kilograms times 9.80 meters per second times her initial height, which is 0.90 meters, plus 1 half times 70.0 kilograms times V initial squared, which is what we're looking for. That's all equal to the final height or the final potential energy, which is 70.0 kilograms times 9.80 meters per second times the final height, which is 5.0 meters. And that's it in its entirety. Now all we have to do is compute those quantities for those terms. So 70 times 9.8 times zero point 0.9 gives me 61.74 joules plus 35.0, and this one would just be kilograms times V initial squared, which is what we're looking for. The other one is 70 times 9.8 times 5 meters, and that gives me 3,430 joules. And I think that's all right. Let me double check my 70 times 9.8 times point 0.9. Oh, nope, I did it again. I actually made this exact same mistake last night. Uh, I put the decimal in the wrong spot. The decimal should be right there between the 7 and the 4. And technically the 3 and the 0 are not sig figs there either. So that's the mathematics of these three terms that we have. So now all we have to do is let's say get the 617 or 617.4 on the other side. So I'll say minus 617.4 joules minus 617.4 joules. And with that, that gives us 35.0 kilograms VI squared is equal to 3430 minus 61 point, oops, excuse me, I almost did it again, 617.4. That gives me 2,813 joules, and therefore we can see that V initial would be equal to the square root of 2,813 joules to 2 sig figs divided by 35.0 kilograms to 2 sig figs. I remember a joule is a Newton meter and a Newton is a kilogram meter per second squared. So a joule is a kilogram meter squared per second squared. So when I divide it by a kilogram, that gives me meter squared per second squared. And then the square root of meter squared per second squared is meters per second. So I'm going to take the 2813 and divide that by 35. That gives me 80.36. Now I'm going to raise that to the 1/2 power. And that gives me 8.964 meters per second is the initial velocity she needs to have. And that is essentially 9 meters per second, which is on the order of about 20 miles per hour. So that's pretty fast. Any questions on that one? All right. I'm gonna do 8-7. I'm gonna skip 8-8 and 8-9, I think. Let me see, 8-8. Yeah, I'll skip that one. This is pretty straightforward. They do a lot explaining you two different ways to do it. So it's a worthwhile example. It's very good, but I really think y'all can benefit a lot just from looking at it yourself as opposed to me working it for you. And the same thing with 8-9. That's pretty straightforward stuff. But it shows you a little bit how to work symbolically. I'm trying to, catch back up, but you can definitely find me working this on some of the other problems on my YouTube channels. But so let's start off with 8-7. It says a dart of mass 0.100 kilograms is pressed against the spring of a toy dart gun as shown in the figure. The spring, with a constant 250 newtons per meter and ignorable mass, is compressed 6.0 centimeters and released. If the dart detaches from the spring when the spring reaches its natural length, x equals 0, what speed does the dart acquire? So again, I'm using my version of conservation of energy, which is UI plus KI plus work in equals UF plus KF plus work out plus E loss. In this case, we are ignoring air resistance, and there's a couple different ways we could treat the spring. We could treat the spring as it's been cocked, so it's work that's been put into the system. But we could also remember that one of the things we did when we first ran into the spring is we calculated a change in potential energy as a result of the spring force, which is Fs equals negative Kx. So we could use it as U. Either one really doesn't matter at all which one you use. So just for the heck of it, I'm going to use U initial instead of work in this time, but you could have done either way. With that being said, we know initially the kinetic energy is 0 because the only energy we have is the energy stored in the spring, which I'm calling work in. So that means U initial is going to be 0. And the main reason U initial is 0, it could be any quantity we wanted. We could say it's M times G times whatever the height of this is. But on the other side, the U final would be exactly the same height because we're just watching the actual dart go from against the spring to just just barely leaving the spring and it's not changing height. So we could say the initial potential energy was 12 or 42 or whatever, but the final one would be the same thing. What we're looking for is the final kinetic energy, or more specifically, we're looking for the final velocity. And there's no work out. We're not further compressing any springs, or we're doing work against friction, and there's no E loss for the same reasons. So in this case, we're gonna get 1/2 kx squared, or yeah, for the work in, that's 1/2 times k x squared is equal to 1/2 times mv final squared. You can see already that the factor of 1/2 cancels out, and that saves us a little bit of work. And now we can say that v final is equal to the square root of, in this case, we're going to have k, and we're going to divide it by m, like that. And then we're going to have that times x squared. Uh, but when we take the square root, that's just going to leave x. So that's our ultimate formula. V final equals the square root of k over m times x, which if you remember chapter 14 and 15, you've seen this formula before. So anyways, here it goes. It's the square root of 250 newtons per meter, which I've written to make sure we know that that's 3 sig figs, and the mass is 0.100 kilograms. So in this case, we're going to have newtons per meter divided by kilograms. A newton per meter is a kilogram per second squared, because a newton meter is a kilogram meter per second squared. So a newton per meter is a kilogram per second squared divided by divided by kilograms, and we get, whoa, wait a second here. Kilogram meter per second squared. Oh yeah, and then times the meter from the x. That's what I was. The units weren't working out, but I was getting per second squared under the square root. The square root of that's going to give per second, and then we multiply that by x, which was, in this case, it was centimeters, but we want it in meters, so I'm going to say 0.060 meters. They only gave us 2 sig figs there, so that's really the limiting factor here. So I'm going to take the square root of, let's do shift square root 250 divided by zero point 0.1, which is 2500, obviously. And that should be basically 50. And that's what we get. And then 50 times 0.06 gives me 3. So the velocity should be 3.0 meters per second. And that's it. Any questions on that one? All right. So that's pretty straightforward. I think you shouldn't have any problems with that. I really think, like I said, problems 8-8 and 8-9. 8-8 teaches you something very important. It's sometimes it's really smart to use a particular spot as y equals 0, which corresponds to potential energy equals 0, and that's largely what example 8-8 is about, because they work it with y equals 0 being the point at which the ball first touches a spring. So the problem is you're dropping a ball, it's going to land on a spring, and that is going to start it slowing down, slowing down, slowing down, even though it was speeding up all the way going down. And in fact, it's sort of fighting, because as the potential energy continues to go down, the kinetic energy is trying to go up as a result of gravity pulling it faster and faster. But now we've got a spring pushing up on it, and as that becomes compressed, that's stealing some of the kinetic energy and some of the potential energy, until eventually, basically, it comes to a complete stop with the spring completely compressed to some point. And what they're asking for in this case is, I think they're asking, determine the spring constant. So you could treat the y equals 0 and the potential energy equals 0 at the first part where it touches the spring, or you could say it's going to be at the very bottom where the spring comes to a stop. And both of those have, redeeming qualities, but they're both a little bit complicated, and you just have to solve it. So I'll leave it at that. I think that's a pretty good explanation of it. The next one is a pendulum where they're working it out in terms of theta. And I think this is worthwhile just for you to look at it. I have been known to give a problem very much like this on my actual tests and final exam. So it's very, very, very likely that it's one that you should know and understand, but I'm going to leave it to you. The big picture is remember that the length of a pendulum is L, and therefore when it swings all the way down, the change in height from being perfectly horizontal to being vertical, the change in height is L. But at any angle theta, the change in height is L minus L cosine theta. So you've got to use that sort of geometry or trigonometry, if you will, to figure out the height, and you can make the function potential energy related to it that way. So that's the big part of example 8-9. So you definitely want to look at that one as well. Both 8-8 and 8-9 are ones that I have put similar problems on tests in the past. But we're going to move on to the law of conservation of energy subsection, and we're going to work some more problems. So, energy conservation, the next problem I want to work is example 810. So let's do that one. So here's example 810. It says friction on the roller coaster. A roller coaster car in example 8-4 reaches a vertical height of only 25 meters on the second hill, where it slows to a momentary stop. It traveled a total distance of 400 meters along the track. Determine the thermal energy produced and estimate the average friction force, assume it is roughly constant on the car, whose mass is 1,000 kilograms. So I'm going to write down the numbers that they gave us. I'm going to draw the diagram, and then I'm going to solve it. So one thing we know is the initial height y initial is equal to 40 meters according to the diagram. And I'm writing that as 40.0 with an underbar so that we can maintain at least the 2 sig figs. The final height is 25 meters. That's clearly 2 sig figs. It traveled a total distance, D, which, by the way, is along the track. And what we're assuming is that the friction force is roughly going to be about the same everywhere. You can imagine it's not really true. Obviously, the friction force is dependent or proportional to the normal force, and you can imagine the normal force is quite different. When it's sitting up at the top of the hill, it's mg. When it goes to slide down, it's mg cosine theta, where theta is the steepness of the hill. And then when it gets down to the bottom, it's not only mg where it's level horizontal there, it's mg plus it's got to provide the centripetal force needed to make this thing go in a circle of arc. So it's not very reasonable to go on the assumption that the friction force is constant, but we're doing it anyway. So the distance traveled along that is exactly at every point parallel to or anti-parallel to the friction force, and therefore friction times distance is going to give us the energy. And as I told you on this version of the conservation of energy law, you don't put any terms in that are negative. You can occasionally like have a height that is negative, so that would make a term to be negative, or the potential energy that we told you for the general equation for gravity is U equals negative GMM over R. That's another time where the term would be negative. But that's pretty much it, is when one of your height values is negative, or when your potential energy has a negative sign built into it by U equals negative GMM over R. The distance I said was 400 meters. I'm going to treat that like it's a full 3 sig figs, even though the other 2 sig figs are probably going to kill it. We also know that the mass of the car is 1,000 kilograms. So again, I'm going to assume that one has 4 sig figs. And what we're trying to do is determine the thermal energy produced and estimate the average friction force. So what we want is what I called E loss. That's going to be the actual energy that goes into friction and therefore is a thermal energy. So E loss equals what they're calling thermal energy. So that's one of the questions. And then the other question is, what is the average friction force? So F with a bar over it is the other question. And I apologize. I wrote that with a bar over it in such a way that the bar looks like it could be one of the digits on there. So I'll write it down here instead. F bar is equal to question mark as well. Solution, we're going to go with U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. It just seems natural for me to use E loss as the kinetic energy term. So that one's not going to be zero. We are going to have an initial potential energy. Let me draw the diagram so you'll have a better idea what we're talking about here. And this height right here from this lowest point on the roller coaster, this height is 40 meters, and then this height where the roller coaster comes to a stop, and I'm going to treat that like that's the center of mass, say that height is 25 meters. So that's the diagram we're going for. The potential energy, of course, is not zero, and reaches a vertical height of 25 meters on the roller coaster on car. Example 4. I'm trying to figure out whether it had any speed when it was at point 1. So let me look back at example 8.4 real quick. Here's example 8.4. The roller coaster starts from rest. That's what I was looking for. So we're going to go back and hopefully. Nope, it's next 2 pages further ahead. Hold on. Take a couple seconds to get back. I'm looking at the book off to the side. I know you guys aren't looking at it, but I want to let you know why it's taking me so long. Okay, there you go. So again, I'm doing this the way that I do with my conservation of energy equation. They're doing it with the way that they do it, and that's fine too. So since we found it was initially at rest, that means K initials equal to zero. We're not saying the motor gave it a push. We're not saying any people gave it a push or anything like that. So work in is going to be zero. The final potential energy, like the initial potential energy, is not going to be zero, but the final kinetic energy will be zero. The work out, which we could count as the thermal energy, that would have been acceptable, but I'm using E loss as the thermal energy. So we're just going to say E loss equals thermal energy as well. And now I'm going to put all those values in and see what we get. So first off, we have 1,000. Oops, let's go back to the green. We have 1,000 kilograms times 9.80 meters per second times 40.0 meters is equal to 1,000. I'm going to leave the units off on this side times 9.80 times 25 plus thermal energy like that. So for the first part where we just want to know the thermal energy, what we're going to do is solve for the thermal energy. So that's just, pretty straightforward. We can get, in fact, that the thermal energy is equal to 1,000 times 9.80 times, in this case, the left-hand side had a 40 meters, and the right hand side, which I pulled to the left hand side, is going to become negative, but that value was 25, so it'll be minus 25.0 meters, and that will be the total thermal energy. So doing that, I get 1,000 times 9.8 times parenthesis 40 minus 25, which is 15. And that gives me, in fact, 100 and no, that gives me 14,700. Ooh, nope, it gives me 147,000. My fault. My calculator's automatically does sig figs, and I'm looking at it, and I keep making careless mistakes by putting it the wrong way. So this will be 147,000 joules is the thermal energy. And of course, we only know it to 2 sig figs, so all these are not sig figs. We'll put that in there. So that's roughly the energy loss due to friction. Now, with that energy loss due to friction, we can set that equal to an average force times a distance, because then that sort of covers up the idea that I was telling you that by treating the friction force as if it's a constant, it's not a very precise way of doing it. But if you think about the total energy loss being consistent with an average friction force times the distance, then you're okay. So now we're going to say uh, the thermal energy equals 147,000 joules, but that's also going to be equal to the average friction force times the distance of travel, which is 400 meters, like that. And what we're using here is E loss is equal to friction force times distance, because they're obviously just parallel. That's what we're really using, are just anti-parallel, which would make it cosine of 180, and a cosine of 180 is just -1. But as I said, we always keep the terms positive here. So our average friction force is going to become 147,000 joules divided by 400 meters, and that's going to give us newtons. So if I take this 147,000 divided by 400, I get 367.5 newtons is equal to the average friction force, and we only know that to 2 sig figs, so we'd roughly call that 370 newtons. Any questions on that one? Pretty straightforward, right? Not too hard. All right, now let's look at example 811, and this one we can just do in the small space that's left, so I think that shouldn't be a problem. So here's example. Whoops, never fails, always does that. This is example 8.11, and what they give us is a block of mass M sliding along a horizontal surface is traveling at a speed of v0. When it strikes a massive spring head on and compresses the spring a maximum distance of capital X. If the spring has a stiffness K, determine the coefficient of kinetic friction between the block and the surface. So this is one of those sort of theoretical type problems where you're working everything out symbolically. And when they give you things like that and I write them down without an equal sign, then that means that, hey, this is the symbol we're supposed to use, and we can go on the assumption, and at least initially, that these quantities are known. So I'm going to pretend like the M, the V0, the capital X, and the K are all known, but then the mu K, which I wrote a question mark equals, that actually tells me, oh, that's the thing I'm solving for. Okay. If we luck out, some of the terms might cancel out, and then we learn something about the physics of the problem, specifically like it didn't depend on mass or something crazy like that. But let me go ahead and draw a diagram of what we're doing here so we'll have some sense of what's going on. So what we have here is a box, and the box actually has an initial speed of V0 just at the instant that it runs into the spring. So I'm going to draw the spring like this, and then all of this takes place on a surface and a wall where the flat surface actually has a coefficient of kinetic friction with the box equal to mu sub k. So mu sub k is the coefficient of friction between the box of mass m And we're ultimately going to compress the spring by an amount X so that it's going to look like this. So that this distance from here to here is capital X. So that's the big problem, and I've drawn it in red so you can sort of imagine that that was is what it's going to look like at some point in future time. Now I'm just going to go ahead and write down solution, and it's U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss, like that. So in this case, you can treat the spring as if it's a potential energy, or you could treat it as if it's some work that the system is putting out. It doesn't really matter. I'm going to actually, this time, since I hadn't done it before, I'm going to treat that as the potential energy because this thing is going horizontally. So I'm not really imagining that the height is going to change. So we don't really need the U equals mgy. But as I say that, I want you to understand that the U equals mgy can go under the U in addition to U equals 1 half kx squared. So when any term in this conservation of energy equation, any one of these terms could actually have multiple parts. So that when I say U sub I, that might just be mgy, but it might be mgy plus 1 half kx squared. All right. I'm going to treat it as if the U is just the spring potential energy, and of course we've got zero spring potential energy initially because the spring is just about to be touched when we start it. The kinetic energy, however, is not zero. The work in is zero because no one's giving it a push or anything. We're just jumping on the scene and seeing that it's moving with a velocity v0. The final potential energy is going to be the 1 half kx squared, and the final kinetic energy is going to be zero. It is going to have some friction. Energy taken away. So we could either call that work out or E loss, doesn't matter, but I'm going to call it E loss because that's what I've been doing. So those are the terms that survive. And now I can write down exactly what they are. I think I've shown enough units where I can. Oh, actually, it don't even matter because I forgot this was symbolic. So you're not going to see the units anyways. So what I have is 1 half mv0 squared is equal to 1 half k and then the capital X squared. And then the energy loss is the friction force, which is mu kinetic times the normal force. And then that friction force times the distance traveled has to be the energy loss. And then, of course, you normally have like a cosine, but we're seeing here that the friction force is obviously anti-parallel to the displacement, and the friction force we're going to treat as a constant. And since it's a level ground, we expect the normal force to just be mg. So this is going to become mu sub k mg, and then, of course, the friction force only applies over a distance x. So we have all that as well. So now what I'm going to do is we're trying to solve for the mu sub k, and we know everything else. I'm going to go ahead and multiply both sides by 2 just to make my life a little easier. And this program's all of a sudden starting to write everything in fancier symbols, or what it thinks are fancier symbols. It always does that. I'm not very impressed with this app for that reason. But anyways, now we've got m v0 squared is equal to k x squared plus 2 mu k m g x, like that. So now I'm going to get all the terms that don't have the mu k in it on one side. So that's going to be m v 0 squared minus k x squared is equal to 2 mu k m g x. So finally, I can solve for mu k. Mu k is going to be equal to m v0 squared minus k x squared, all of that divided by 2 times m times g, which I could break that up into separate terms. And in that case, I'm going to get v0 squared over 2g because the m's cancel out, and then minus, make sure I got everything there. It looks like I do. Oops, I left the x off on the bottom. And there it goes, drawing a better version of it for me. Okay, there was an X that was supposed to go in the bottom. I just neglected to write that down for whatever reason. Now the other term becomes kx squared over 2mgx. So one of the x's cancels out. That gives me kx over 2mg. And that's basically it. So mu sub k is going to equal v0 squared over 2g minus kx over 2mg. You might notice kx is the actual force of the spring, and is actually the weight. So the kx divided by twice the weight is one term, and the v squared over 2g looks like something from kinematics. But other than that, you can't really make any grandiose conclusions about what this is, but that is the formula for the answer. Any questions on that? Oh, the X was left out of the other one, by the way. Remember that X was in the denominator. So because of that, let me just write it in here. You see that I just put an X down there? I'd left that off as well. So there's an X that goes in this as well. So remember when I forgot to divide by x on both sides, that meant both of the fractions should have x in the bottom. So that was missing. And now it looks more like v0 squared over 2ax, which is part of the kinematic equation I was talking about. All right, so that's it. I got v0 squared over 2gx minus kx over 2mg. That's
I do
the
have a
answer.
quick question.
Yeah, Michael.
So, because I have the textbook on the side here as well.
Hmm.
On the UK, it's equal to v squared over 2gx.
Hmm.
And I noticed that you put an m. I was just curious as to why the m was getting placed there.
So the m was part from the kinetic energy. So we had mv0 squared in this part,
The initial,
and
yeah.
then we had that m over there as well. Not all three of the terms had m in it though, so we couldn't just get rid of the m. So what I tried to do is get the mu k term on one side of the equation and all the other terms on the other side. And then what you have to do is divide out the 2, the mgx. I divided out the 2 and the mg, but I left off the x. So that's where that came from. And then when you divide this part, you can see that the m cancels out with the m, and that just gives v0 squared over 2gx.
Okay, I see.
Does that make sense?
Those
Yeah.
are
It doesn't help when I drop a symbol in doing the symbolic algebra. So, uh, anyways, any questions on that?
nope.
Good deal. Good question. Work versus energy conservation, blah, blah, blah. All right, we're going to move on to the gravitational potential. I did actually give you an idea of how to derive that before. Uh, the result we got was U is equal to negative GM M over R. So I'm just going to make use of that now. You can also check the derivation, or you can check last night's video. I redid this derivation to find out that the potential energy in section 8.7 is U is equal to negative GM over R. And that's for any planet. The big thing to know here, though, is this only goes for R's greater than the radius of the planet that you're talking about. If you wanted to talk about the potential energy at a radius smaller than the radius of the planet, you could do it, but you'd have to use what we learned about the spherical shells when we just introduced the law of gravity. Specifically, the shells dictate that basically only the matter inside of the shell are inside of the sphere at a radius greater than the distance away. only that mass matters in computing the force or the potential energy of the object. So if the object's out at a radius greater than the planet, then the entire mass of the planet counts. But if the object that you're wanting to calculate the potential energy or the force of gravity on is at a radius smaller than the radius of the planet, then it turns out only the mass between r equals 0 and r equals whatever the object's at, only those masses matter. So you have to sort of lessen the mass by whatever parts or whatever spherical shells are further away from the center than the object, because those masses are not going to play any role in the force or the potential energy. So you can actually do it. It's just not that relevant, because when you get to 242, we're going to do the exact same thing with an exact same force. In other words, the gravitational force is G-M-M over R squared, but we're going to do that with the electric force, which is Q or K Q Q over R squared. So it's literally the same thing, and we'll learn a way to do it. So they're just saying we don't need to do that right now. The other thing is when you do use U equals negative GMM over R, that is going on the assumption that basically the potential energy normally is assigned to be zero at R equals infinity. But in principle, you could say it's plus any constant, because ultimately it's only the change in potential energy that matters. So now that we have that, I want to, one, give you a little potential energy function. So U sub G of R is negative G M. And if we're talking about Earth, then this mass is the mass of the Earth. And this R is the distance away from the center of the Earth, not from the surface of the Earth. Okay. And then additionally, if you wanted to make a plot of potential energy versus R, what you'd see is that we have to ignore R equals R Earth. We can't do anything any smaller than that. But what we do see is that the potential energy sort of goes like this and asymptotically approaches zero. So that's what the potential energy curve looks like. But I'm saying by putting this right here, I'm saying I can't say anything about what that function is specifically, because I haven't addressed the idea of how the potential energy changes for a smaller radius than the radius of the planet. All right, now that we have that, we're going to jump into example 812. So let's do that. Example 812 says a box of mass m is allowed to fall from a rocket traveling outward from Earth at a speed of 1,800 meters per second when it's 1,600 kilometers above the Earth's surface. The box eventually falls through the Earth. Estimated speed just before impact. Ignore air resistance. So we have a box of mass m. Notice I'm just writing the m there, and I'm not writing any equals. So we're assuming we know it, and hopefully it'll work out such that the m disappears. If that's so, then yay. Um, but we also know that initially it has a velocity vi equals 1,800 meters per second, because this box is on a spacecraft, and that spacecraft is traveling away from the Earth radially outward at 1,800 meters per second. So if you just stick the package out and just let go of it, it's still automatically going 1,800 meters per second because it was riding with it. We also know that its initial height, y initial, is actually equal to 1,600 kilometers above the Earth's surface. So I want you to remember that that is an altitude. That's not the distance from the center of the Earth, and it's 1,600 kilometers. I also want to point out that the radius of the Earth is 6.378 times 10 to the sixth meters, which is 6.378 times 10 to the third kilometers. So that's something else that comes in handy. 6.378 times 10 to the third kilometers. Because of that, you can line that up better with the 1,600 kilometers to see exactly how far it is from the center of the Earth. And what we want to do is figure out its speed just before impact. So we want to say V final is equal to question mark, what we know is y final is just equal to the radius of the, or excuse me, is just equal to 0. Since we're using y as an altitude, it's 0 like that. Our solution says u initial plus k initial plus work in is equal to u final plus k final plus work out plus e loss, like that. Now we're going to just piecewise take all the functions and put them in. We are going to assume that the work in is 0 because we don't care what kind of work was done to reach that 1800 kilometers at six or meters per second at 1600 kilometers. We do know it has an initial kinetic energy. We do know it has an initial potential energy. And we also know that it has a final potential energy and a final kinetic energy. So none of those is 0. We are ignoring air resistance. We're not going to run into any springs to catch us. So all of those other terms are 0. I'm going to leave the units off. We can think about the units as we're doing it, even though we don't have the units. And that is definitely something you want to do. I'm just going to leave the units off to save space and time. So the potential energy initially is negative. Notice this is a chance where we're actually going to have a negative term, and it's because the potential energy function is defined to have a negative term. So it's going to be negative 6.67 times 10 to the negative 11th. That's the G. We're going to have the mass M that we're just assuming we know in hopes that it might cancel out. We're going to have the mass of the Earth, which is 5.98 times 10 to the 24 kilograms. I didn't give you that, but I should. Let me write that down. M Earth is equal to 5.98 times 10 to the 24 kilograms. That's where that came from. And then all of this will be divided by the height that it actually has plus the radius of the Earth, because the distance from the center of the Earth is the radius of the Earth plus the altitude. So what we're doing is we're saying 6,378 kilometers is the radius of the Earth, and we're adding to that 1,600 kilometers. So this is going to be 7,978 times 10 to the third meters. So notice I just took the 6,378 and added 1,600 to it, and that made it 7,978. Does that make sense? Now we're going to say plus the kinetic energy, which is 1/2 m, and then this is 1,600, or excuse me, 1,800 meters per second. That's going to be squared. So that's the two terms on the left. The two terms on the right are going to be negative 6.67 times 10 to the negative 11 times m times 5.98 times 10 to the 24. All of that's going to be over 6,378 times 10 to the third meters. And actually, I don't need to put those meters in there because, as I told you, we were leaving the units off. And we're wanting to figure out what the final kinetic energy is. So we also have plus 1/2 m v final squared. Now we can see that the lowercase m, we can divide both sides by lowercase m, and all of the lowercase m's are going to cancel out. We can also take and multiply both sides by 2, like that. And in so doing, that'll get rid of the pesky little 2. And now I'm going to get, for each of the terms, I'm going to compute them. I'm going to say negative 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. And then I'm going to divide that by parentheses. I don't even know why I use parentheses. 7,978 times 10 to the third, close parentheses. So this gives me negative 9.999 times 10 to the seventh. And you can tell since it's a potential energy term, but it's a potential energy term without one of the masses, so it should be joules per kilogram. So that's what that unit is, just in case you're wondering. We did get rid of the 1/2 in the kinetic energy by multiplying by the 2. So this is just going to be 1800 squared in that term. So 1800 squared is going to be 3,240,000. So plus 3,240,000. And that one happens to be joules per kilogram as well. And then the right hand side is going to be 2 times negative 6.67. So I'll say negative 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th. And then I'm going to divide that by 6.378 times 10 to the, or 6.37, yeah, times 10 to the third. Just making sure I did that on the other one as well. And that gives me 1.251. So that's literally 125100000 joules per kilogram is that figure. I want to double check, make sure I put that last value in properly. 2 times 6.67 10 to the negative 11 times 5.98 times 10 to the 24th divided by 7978 times 10 to the third. Yeah, I did do that right. And then finally, we multiplied by 2 so that 2 is not there, but I just get V final squared there. So now what I'm going to do is I want all the terms that have, oh, and this is a negative 2, by the way. Don't forget the 125 million, that's actually a negative. So now what I'm going to do is I'm going to pull the 125 million to the left-hand side with the negative 9.99 times 10 to the 7 and the positive 3 million. So I'm going to say, oops, I'm going to say times, oops, it won't let me do that. Let's say shift answer times negative 1. Okay, so now I've got the positive 125,000 or 125,100,000. I've got that positive, and now I'm going to subtract from it 9.999 times 10 to the seventh. And now I'm going to add to that the 3,240,000. So plus 324,000,000. That gives me the left-hand side 2.833 times 10 to the seventh joules per kilogram is equal to V final squared. And remember, a joule per kilogram is a Newton meter per kilogram, and a Newton meter is a kilogram meter squared per second squared. So a joule per kilogram is just a meter squared per second squared, which is exactly what we expect. And that gives us that V final is equal to the square root of this number. So I'm going to raise that 2.833 times 10 to the seventh. I'm going to raise that to the zero point 0.5 power, and that's going to give me 532. Oops, nope. 5,322 meters per second. And of course, we only really had, in terms of sig figs, we had 3 at best. So I would probably say that's roughly about 5,300 meters per second, or maybe 5,320 meters per second, depending on your sig figs. But you can tell that's on the order of 10,000 miles per hour, so it's pretty darn fast. Any questions on that one? All right. Now I'm going to do the next example, which is 813, and this one's about escape velocity, and they did a derivation of escape velocity. So I'm going to start off this problem by doing a derivation of escape velocity within the problem itself. So let's look at example 813. So example 813 says compare the escape velocities of a rocket from Earth and from the moon. So compare V escape Earth and V escape moon, which we can do like that with a little crescent symbol. That's often the case. And then B, that's part A. Part B, they want us to compare the energies required to launch the rockets. So compare K escape Earth and K escape crescent moon. So that's what we're shooting for. Now, what is the escape velocity? The escape velocity is the lowest velocity you could give something at the surface of the planet such that it would just lose its last bit of kinetic energy as it reached infinitely far away. So as r approaches infinity, it's slowing down, slowing down, slowing down, and in fact comes just to a stop when it gets to r equals infinity. At that time, of course, the potential energy is also zero because the limit as r approaches infinity of negative g m over r is zero. So the way we go about doing this derivation is the following solution. And we're going to use ui plus ki plus work in is equal to u final plus k final plus work out plus E loss. Okay, we're ignoring air resistance and all that crazy stuff. So work in, we're not considering what got it up to that speed. Work out, we're not considering it bouncing off a spring or anything like that. E loss, we're ignoring air resistance. And in fact, since I told you the way the escape velocity works is you take off from Earth with both potential and kinetic energy, but you get out infinitely far away so that your potential energy is zero. And just as you reach that infinitely far away, the kinetic energy is zero as well. So that means these two sides are zero too. So I'm going to work this out for Earth. And then from that, you can make the transition of seeing what the formula would be for the moon. So the potential energy initially is negative. I'll stick to my purple. It's going to be negative g times the mass of the object doing the escaping times the mass of the Earth, which is the m with the plus symbol in a circle. And it's taking off from the radius of the Earth. So I'm going to put r circle with a plus in it down there at the bottom. The kinetic energy is going to be 1/2 m, and this time it's going to be v escape for the Earth squared, and the other side is just going to be equal to zero. Now you can see the usefulness of that negative. We're not going to get any square roots of negative numbers, and in fact, what we can figure out is we can divide both sides by m, and that means the lowercase m disappears, and this result is independent of the mass of the spacecraft. So therefore, we get v escape for Earth is going to be equal to the square root of 2g mass of the Earth over r of the Earth. That is the escape velocity. And you can tell, therefore, that v escape for the for the moon, which is me drawing a little crescent there, is going to be equal to square root 2g mass of the moon divided by radius of the moon, like that. So that's the two quantities. When they ask you to compare, often the most useful way of comparing is by division. So you can take the velocity, the escape velocity of the Earth, which you expect is a lot larger than the escape velocity from the moon. If you've even read a little bit of the history of us going to the moon, you know that. But if you also think about it, you know the mass is higher. That's going to make the velocity a little bit larger because the larger mass, the larger the escape velocity is going to have to be from the formula. But you do know that the radius is smaller. for the moon. So that could make it possibly larger, but it's not as big enough a difference to make it matter. So what we're going to calculate is V escape for the Earth divided by V escape for Luna. And that's going to be, since both of them are under a square root, we can write one big square root. And then the top one's going to be 2g mass of the Earth over radius of the Earth, and the bottom one's going to be 2g mass of the moon divided by the radius of the moon, like that. You can see that the 2 and the g cancel out with the 2 and the g, and we end up getting a square root of specifically the mass of the Earth times the radius of the moon divided by the mass of the moon times the radius of the Earth. Now we can plug all those values in. The mass of the Earth is 5.98 times 10 to the 24. The radius of the moon is 1.74 times 10 to the 6. Notice the problem's giving you that, and obviously you'd be given that on a test problem as well. And that's in meters, and in that case, in the 24 was in kilograms. Now we're going to take the mass of the moon, which is 7.35 times 10 to the 22 kilograms, and we're going to take the radius of the Earth, which is 6.378 times 10 to the sixth meters as well. So all we have to do now is do all that multiplication and then take the square root, and that's 5.98 times 10 to the 24 times 1.74 times 10 to the 6 divided by parenthesis 7.35 times 10 to the 22 times 6.378 times 10 to the 6 close parenthesis. That gives me the square root of 2.22 or 22.20, and that's a pure number. There's no units left at that point. Now I take the square root of that by raising it to the point 5 power, and that is 4.711. We only used really 3 sig figs, so we can't call that a sig fig, so we have to just say it's 3 sig figs. So now what we know is the escape velocity of the Earth is equal to 4.711 times the escape velocity for the moon. And that's supposed to be my little crescent there. And that's the answer for part A. Now for part B, we want to know the kinetic energy. So the kinetic energy comparison is as follows. Again, we're going to use division. So K escape Earth divided by K escape crescent or moon is equal to 1/2 times the mass of the Earth times the square of the escape velocity, which would be 2 g_m Earth over radius of the Earth. And then the kinetic energy of the moon is 1/2 mass of the moon times v squared, which would be 2 g_m of the moon divided by r of the moon, like that. And you can see here that the 2, the g, and the 1/2 cancel out with the 2, the g, and the 1/2, and our result is in fact equal to mass of the Earth squared times the radius of the moon divided by the mass of the moon squared times the radius of the Earth. So we can compute all that by doing 5.98 times 10 to the 24 squared times 6 point, oops, nope, that's 1.74. 1.74 times 10 to the 6th over. Now the mass of the moon was 7.35 times 10 to the 22. That quantity is going to be squared, and the radius of the Earth is 6.378 times 10 to the 6th. That'll be like that. So now we can get 5.98 times 10 to the 24 squared times 1.74 times 10 to the 6. All that divided by parentheses 7.35 times 10 to the 22 squared times 6.378 times 10 to the 6 close parentheses, and this gives me 1,806. Oopsie. I was Okay, so we're off a little bit here. Let me explain what I just did. I was trying to calculate the kinetic energy of the spacecraft, but I inadvertently put in the mass of the planet for the mass of the spacecraft. So this is what's wrong right here. That and that are just supposed to be m's, and they're going to cancel each other out. So sorry about that. That's a really bad mistake. Let me fix it. The way I'm going to fix it mathematically is we're going to get rid of the 2, we're going to get rid of that 2, and we're also going to get rid of this 2, and of course we're going to get rid of that 2. And the reason why we're getting rid of those 2's is because these quantities were not there. Those quantities were supposed to be, I'll write them in red so you can see what happened. That was the mass of the individual spacecraft that we're imagining. And now what we can see is that mass and that mass cancels out. And instead of 1,806, which was a pain in the butt to calculate, we have a much easier thing to calculate because it's just the mass of the planet times the radius of the moon divided by the mass of the moon times the radius of the earth. So let me recalibrate that. That's 5.98 times 10 to the 24 times 1.74 times 10 to the 6 divided by parentheses 7.35 times 10 to the 22 times 6.378 times 10 to the 6 close parentheses, and this gives me 22.20. So in this case, what we see is the escape kinetic energy for the Earth is about 22.2 times the escape kinetic energy for the moon. And that's what we're shooting for. You might notice also that 22.2 is very much close to 4.71 squared. So that's the big difference there. Any questions on that one? Sorry about making that booby with the mass. I wish I would have caught it beforehand, but anyways, it was a pain to calculate too with all those squares and all that junk. So you can see they got 4.7 and they got 22 for the values if you're looking at the actual book problem. And let me see what else. Oh, we did do power. I actually did cover what power was, but I didn't work these examples. So I'm going to work those real quick, and then that'll be the last of what we're doing in chapter 8. And hopefully that'll give us enough time to get into chapter 9. So let's look at example 814. Don't forget, Michael, we do have a test this weekend. That's due on the 5th. So make sure you do that. Don't want you to miss that. Now it's on the video too, so hopefully it'll help the people that aren't here. What we have is a 60-kilogram jogger runs up a long flight of stairs in 4.0 seconds. The vertical height of the stairs is 4.5 meters. Estimate the jogger's power output in watts and horsepower, and then B, how much energy did this require? This is a brutal thing. Have you ever tried running upstairs for exercise? Whew. I did that for a little while, and I realized that I was probably going to die of a heart attack, so I stopped doing it. But the day that I stopped doing it, I was out running at the soccer stadium at Chapel Hill, and I looked and I saw Coach Guthrie, Bill Guthrie, who was then the coach for UNC Chapel Hill right after Dean Smith had retired, and Ed Cota was our point guard, and he was. I think it was point guard. But anyways, those two guys were running together. It was crazy to see Guthrie, as old as he was in his 60s at the time, and Ed Cota, who was like 22 and, a really good basketball player, but they were running together up the steps at the stadium for the women's soccer field. I was like, holy crap. I couldn't handle that for nothing. But so anyways, the mass of the jogger is 60 Point zero kilograms, but I'm treating that as if it's two sig figs instead of three. I'm making a transition where I start doing that more since the author does it so much. The delta T is going to be 4.0 seconds, and the delta H or delta Y is going to be 4.5 meters. But we could say the Y initial would be zero. That's another way of thinking about it. And then for part A, they want us to estimate the jogger's power output. So P in watts equals question mark, but we also want P in horsepower equals question mark. And then part B, they want to know how much energy did this require. So delta E equals question mark. You could also say, let me go ahead and erase that last question mark. We could also say that's delta U or U final, either one. All of those are the same thing. So what we're going to use here is solution. What we know is power on average is delta W over delta T, but it can also equal delta U over delta T, and it can also equal delta E over delta T. Of course, instantaneous power is dW over dt, which would also be du over dt, which would also be dE over dt. And there's another formula that I derived last time when the force is a constant and the velocity is a constant. You can get P equals F dot V. That's a real one, but it doesn't come in handy here, so I'm not writing it down. So let's start off with part A. What we want to know is the power in watts, and the power is equal to the change in potential energy, which in this case is mgy, or more specifically, let's write that as mg delta y, and then that divided by delta t. So we're going to get 60.0 kilograms times 9.80 meters per second times delta y, which would be 4.5 meters, like that. And then all of this happened in a minuscule 4.0 seconds, which, good for that lady there. 60 times 9.8 times 4.5 is equal to, and that's going to come in handy in a second. That's why I'm taking time to write it. This is 2,646 joules. And of course, that's only good to two sig figs, so I'll underline the 4 and the 6. And then that's divided by 4.0 seconds. So now I'm going to divide that quantity by 4, and that gives me 66.15. So P is equal to 66.15 watts. But of course, that's only to two sig figs, so that's why I underline the other two. And now I'm also going to realize that we could take this number and multiply it by specifically 746 watts is equal to 1 horsepower. So that's a conversion factor that would actually be in the inside cover of your textbook. And if you've looked at the test, you'll notice that that's the data that's given at the bottom of the test on both the online and the fast and the face-to-face test. So we're going to do that now to go ahead and convert it to horsepower. So I'm going to take the 66.15 and divide it by 746, and that's going to give me 0.8866 horsepower. So we now know that the power is about 66 watts or about 0.89, oops, about 0.89, dang it, still the wrong color, 0.89 horsepower. Okay. Now, how much energy did this require? Remember that B power on average is delta E over delta T. So you can say that delta E is equal to P bar delta T. So with that in mind, you can go ahead and say, all right, I'm going to take the power, which is 66.15 joule or watts, excuse me, and I'm going to multiply that by 4.0 seconds, and 66.15 times 4, oops, 66.15 times 4 gives me, in fact, 26 or 264.6 joules. And remember that, of course, you actually are only, well, never mind. I'll leave that be. I'm going to go ahead and underscore the 4 and the 6 because those are not sig figs. And this is the energy. So I'll write equals E and I'll circle it off. So we now know that the energy was about 264. Let me double check this. 60 times 9.8 times 4.5. So I think this is supposed to be 2,646, not 264.
I believe it's the decimal place under the wattage of 66.15.
Oh, is that what happened? Gotcha. So when I did 2,646 divided by 4, yeah, I got 600. That's what it was. Thanks. Nice correction on that. That means that this, I got to stop putting this calculator in scientific notation because I keep reading it wrong, which is a brain fart on my behalf, but it's something that definitely shouldn't be screwing me up every time. So this should have been, in fact, 661.5, and then does that make the horsepower is going to be? Yeah, it's going to be more like 1 horsepower or something like that. No, that actually. So six six. Oh, that's right. Because I took the 661.5. It was already in my calculator, and I just divided it by 746. So it actually gave me the right answer of 0.886. But the 661 was just me misreading the number. And the same thing happens here. Is I misread the number uh, in this part as well as in this part. So I'm going to write this as 661.5, underlining the 1 and the 5, and 2,646, like that. So it's actually 2,646 joules is the energy, and that's more like what the book had, which was 2,600. Sorry about that. I got to pay closer attention, or I'm gonna take my calculator out of scientific notation mode because it's obviously wreaking havoc on me. All right, there's one more problem, and this one's much more complex, and I like it, so I'm going to go ahead and show you that. That's example 815. So example 815, power needs of a car. And it says calculate the power required of a 1,400 kilogram car under the following circumstances. A, the car climbs a 10-degree hill, a fairly steep hill, at a steady 80 kilometers per hour. And B, the car accelerates along a level road from 90 to 110 kilometers per hour in 6.0 seconds to pass another car. Assume the average retarding force on the car is 700 newtons throughout. So that's like taking into account friction and air resistance, mostly air resistance, but friction would be relevant as well. So I'm going to write down what we know. We know the mass of the car is 1,400 kilograms, and it appears that car looks a little bit Porsche-like to me, maybe Porsche 944, something like that. The angle theta is equal to 10.0 degrees. I'm going to force this to be 3 sig figs, and it's at a steady V. And I'm going to call this part A because we're talking about the angle and stuff. So A, the velocity is going to be 80 kilometers per hour. And of course, we need to convert that to meters per second. And all you have to do that is divide by 3.6 because 1 meter per second is 3.6 kilometers per hour. And then for part B, oh, actually, we want to know specifically the power required. So P is equal to question mark. And then for part B, they're saying the car accelerates along a level road, so theta is equal to zero point 0.0 degrees, but V initial is 90.0 kilometers per hour. I'm going to assume that other one was 80.0 as well. And the initial velocity is 90 kilometers per hour, and the final velocity is 110 kilometers per hour. I'm going to assume that it has 3 sig figs, and the delta t in this case is 6.0 seconds. And actually, I'm going to call that 6.00 seconds. And we're saying F, the retarding force, is 700 newtons, and I'm treating that as if it has 3 sig figs as well. Okay. So let me draw a little picture of this to get an idea. First off, for part A, well, actually, let me go ahead and do this too. Solution. We're going to use the summation forces is equal to mass times acceleration. That's Newton's second law. We're going to have to use that. We're also going to have to use power is equal to F dot V because it turns out when the force and the velocity are constants, then you can just do the dot product F dot V to get the power. So that's what we're going to use in this case. Now for part A, I'm going to draw the incline like this. So this is 10.0 degrees equals theta. The car, not quite Porsche-like in my drawing, but still, I'll draw the free body diagram on this diagram. So that's my x-axis, and that's my y-axis. And the forces acting on it are going to be there's a force that's actually created by the engine of the car, and that is pushing the thing forward, and that's a green vector because it points in a positive coordinate direction. Then there's a force of friction or a retarding force that points in the negative direction. So that's a red vector right here. I'm just going to call the green one just plain F, and that's the force that the ground is applying to the tires of the car as a result of the tires trying to rotate as a result of the engine trying to accelerate them. And this red is the retarding force, F sub R. Now, in addition to that, we have the weight, which is just M times G at this angle theta, but that has to be broken down into components. And in fact, it's going to have a negative Y component right here that is mg cosine theta, and it's going to have a negative X component, which is mg sine theta, like that. And we're also going to have a normal force acting upward on it, and that's Fn. So that's all the forces acting on it. However, we don't necessarily have to break everything down. In this case, we just got to figure out what that force F is that's applied to the car because that, when we dot it with V, which by the way, they have to be parallel, so the dot product is just F times V. They have to be parallel because they're both going up the incline. So with that in mind, I'm going to take the summation of the forces in the X direction equals mass times acceleration in the x direction. And in this case, we're actually asking for it to go a steady speed of 80 kilometers per hour. up the incline. So the acceleration is by necessity or by definition zero. So what we get is F minus 700 newtons, that's the F sub R, minus mg sine theta is equal to zero. So we get that F has got to equal 700 newtons plus 1400. I'm going to leave the units off here for obvious reasons. Times 9.80 times the sine of 10.0 degrees. Don't know why I left that unit on there. But anyways, now that's the whole thing, right? Make sure I haven't missed any. I got the friction force. I've got the mg sine theta. Yep, that should do it. So now I'm going to say 700 newtons and then 1400 times 9.8 times sine of 10 gives me 2,382. So plus 2,382 newtons. This is 3 sig figs, so that one's digit is not a sig fig. And therefore, this turns out to be 3,082 newtons roughly. So that should be the actual force that we're working with. And now I can use P, and that's not a vector, by the way. I can use P is equal to F dot V, but since F is parallel to V, that's just F times V. And that means F, which is 3,082 newtons, times V, which is 80.0 kilometers per hour, times 3.6 kilometers per hour is equal to 1 meter per second. So I can multiply all this by going 3,082 times 80 and then divided by 3.6 gives me 68,500 watts is the power. 68,500 is the power we got there. Now I'm going to go ahead and work that out. So power, which we already calculated, is 68,500 watts. And I want to express that it's only the 3 sig figs, so these two are not sig figs. But now I'm also going to convert it to horsepower because 746 watts is equal to 1 horsepower. And therefore we get, when I divide this 68,500, when I divide it by 746, I get roughly 91.82 horsepower. Now, in this case, the engine of a car is only about 60 to 80% efficient. So you'd actually have to divide that by as small a number as zero point 0.6, in which case that would come more like 153 horsepower, or divide it by zero point 0.8 because it's 80% efficient. And if I divide that by zero point 0.8, I get more like 115 horsepower. So somewhere between 114, 115 and 153 horsepower is really what the car would need to be in order to go up that 10-degree hill at maintaining at 80 kilometers per hour with this kind of retarding force. Any questions on that one? Now, part B, they're asking us sort of the same thing, but instead of having a 700 Newton retarding force and an mg sine 10 degrees retarding force, in this case, we're actually going to have an acceleration. So, and it's on level ground, so we don't have to worry about any angle whatsoever. So for part B, I need to calculate the acceleration first, and the acceleration is v final minus v initial over delta t. And that, of course, is equal to the final velocity is 110 kilometers per hour. You can convert that if you want first, but I'm going to do it separately. It turns out to be about 30.6 meters per second. and then minus 90.0 kilometers per hour. That turns out to be 25 meters per second. But what I'm going to do is do the subtraction and then multiply by 1 meter per second per 3.6 kilometers per hour. I know I couldn't have written that any smaller. Uh, Let me make sure everybody sees what I have written here. That's 3.6 kilometers per hour in the denominator, and that is 1 meter per second in the numerator. So that's what's going on there. And then I'm dividing all that by, if I remember correctly, it's 6 seconds. Yeah, 6 seconds. So I'm going to divide all that by 6.00 seconds. So 110 minus 90, of course, is 20. So 20 time or 20 divided by 3.6 gives me 5.556 meters per second divided by 6.00 seconds. And that gives me 0.9259 meters per second. So that's our acceleration. Of course, I carried one extra sig fig there. So you can see 0.9259 meters per second is the acceleration. And therefore, from the summation forces is equal to mass times acceleration, we get the following. F minus 700 newtons is equal to 1400 kilograms times 0.9529, or excuse me, 9259 meters per second. And this allows us to figure out that F is going to be equal to 700 newtons plus 0.9259 times 1400 gives me 1,296 newtons with one extra sig fig there. And that's the force. So now I can use P is equal to F dot V, but they're parallel, so that becomes F times V. And what we're going to use is the velocity that it had at the end, which is the 30.6 meters per second, or 110 divided by 3.6 gives me 30.6. So this is going to be uh, 1,996 because when you add the 700, it becomes 1996 instead of 1296. So it's 1996 newtons times 30.6 meters per second. And I'll just point out that this is 110 kilometers per hour times 3.6 kilometers per hour divided into 1 meter per second. That's where that came from. So if I multiply, well, first I add 700 to the 1296. That gives me 1996. And now I'm going to multiply that by 30.6. And that gives me 61,090 joules, or excuse me, watts. So the power in this case is 61,090 watts, but we also want that in horsepower. So I'm going to say times 1 horsepower is 746 watts. So I'm going to divide that 61,000 by 746, which gives me 81.89 horsepower. So this one's closer to 82 horsepower, which again, divide by zero point 0.6 and you get a little bit larger, or divide it by zero point 0.8, you get a little bit less larger. But anyways, that's the actual answers. Any questions on that? All right. So that's the end of chapter 8. And in fact, we only got about 16 minutes left. So I'm going to try to get you a little bit started into chapter 9. Uh, but I will recommend people watch the video from last night, which should be, if you do a search for PHY241N02B, I'm going to write this down here. So search my YouTube channel for PHY241N02B. And actually, you don't even have to include this part. Really, what you need to include is this last part, which is yesterday was 06302026, and there will be actually no there will actually be two of them that pop up. One will have a different PHY241 number in it. It'll have a 002B, and that's an intro to lab. You'll know that's not the right one, but the one that has the NO2B is about momentum and all this other stuff. So it covers all these examples we just did, but if you scroll to the end of it, you can see the opening parts of conservation of momentum. So search that for this and watch. Oops, I don't know what that word was. Watch. WATCH, the last 25 to 30 minutes. Mainly what I'm wanting you to watch is the conservation of momentum part. So what I'm going to do is get you started on making some sense of the chapter on momentum. Linear momentum is what they call it. And to do that, let's go ahead. The chapter is called, as I mentioned, is just called linear momentum. So let me break this off with a nice line here. Chapter, whoa, that's not helpful at all. Chapter 9, linear momentum. Okay. So that's the topic. Now, what I'm going to start off with is tell you that what we've been treating as Newton's second law is a version of Newton's second law, but specifically speaking, it's not what Newton gave us in his Principia. What Newton gave us in his Principia is more general or more correct. In fact, what we've been using, F equals ma, or summation of the forces equals mass times acceleration, that is a specialized version that's only true if the mass of the object that you're applying it to is not changing. In reality, there's a second term instead of just ma, there's another term that has to come into play if the mass is changing. So, what Newton actually gave us was the following: the summation of the forces, which you normally just call the net external force, but I always write it with sigma and F just to remind you that you got to add up all the forces. Well, that turns out to not be equal to MA, but rather it's going to be dP over dt, where P is defined to be mass times velocity. That P is momentum. It's specifically linear momentum. So P equals mv is linear momentum, and we can apply this to a single object of mass m with velocity v. That's fine, but we can also apply it to a system like a flock of birds, for instance, in which case the total momentum P would be m1 v1, which is the mass of the first bird times the vector velocity of the first bird, plus m2 v2, which would be the mass of the second bird times the velocity of the second bird, vector velocity, so on and so forth. And you can do it that way as well. Only when you do that, if you find that bird 1 bounced into bird 12, that's an internal force. That's a force that bird 1 applied to bird 12. And then there's also a force that bird 12 applied to bird 1. Both of those are internal forces and they never appear on the left-hand side of Newton's second law. So that's another advantage is you don't have to take into account when parts of the system are applying forces to each other. Now, what makes conservation of momentum? Well, let's say conservation of linear momentum. So this is conservation of linear momentum. If the net external force is equal to zero, then the summation forces is equal to dp dt implies that dp dt is equal to zero. Therefore, whenever you take the derivative of something with respect to time and you get zero, that means that the thing that you were taking the derivative of must have been a constant. So, in fact, you find that P is equal to a constant. It's a constant vector, but it's still a constant. So, it has a fixed magnitude and direction. Now, you can rewrite that other ways. Specifically, you could say, therefore, P initial is equal to P final. And that is the way we normally interpret conservation of momentum is P initial equals P final. Okay. So it's not only that we need to know what conservation of momentum means, specifically P initial equals P final, but you also need to know under what conditions is linear momentum conserved. And this tells you that if the net external force acting on the system is zero, then dp dt equals zero and p equals a constant. So linear momentum is conserved only when the net external force is equal to zero. Does that make sense? Okay, so that's a big part that you have to know. So if I ask you what is conservation of linear momentum, you'd say P initial equals P final, and I'd only give you about half credit. But you'd say under circumstances in which the net external force acting on the system is zero, then the P equals a constant, which tells us P initial equals P final. Now, I want to give you something else about Newton's second law here. We can take Newton's second law, let's do it this way, say another facet of N2. And what that is we're going to take the summation of the forces, which equals dp dt, and I'm going to take and multiply both sides by dt. And then I'm going to integrate both sides like that. From that result, we get delta P, which equals the integral of dP from P initial to P final, and these are vector quantities, has to be equal to, because notice the right hand side, the integral of dp dt times dt, the dt's look like they're canceling out, and that's what I'm saying here. They do cancel out. The parts of what we treated as the symbol to represent derivatives, the dp and the dt, those are actually things. They're not just part of a symbol. They're actually things. As I mentioned before, they turn out to be one forms. So you can actually sort of picture them canceling out and stuff like that. But that's what the right hand side is. Now, the left hand side, which is equal to it because it is the left hand side and right hand side of an equal symbol, is also the integral. Oops, meant to write that in red. It's also the integral from t initial to t final of the total force dt. Now, both of these, delta p equals the integral from P initial to P final of dP. That is equal to the impulse. Oops. That is equal to the impulse, which we give the symbol J, but the impulse is also equal to the integral of the summation of the forces dt from t1 to t final. So that's the impulse as well. The impulse really is a change in momentum, but it can also be the sum of the integration of the net force over time from some T1 to T2, and that's another quantity that we need to make use of. So I just wanted to give you that idea here, in addition to the conservation of momentum, linear momentum, which is this box, and Newton's second law, which is this box, along with the definition of linear momentum, which is that. Does that make sense? All right. Now that we have that, we can do some very specific examples just to get us started. I'm not going to talk about what the subsections are because that takes too much time, but I will tell you that section 910 is systems of variable mass rocket propulsion. I've tried to get rid of all those questions from the practice tests and the homeworks, but they might still appear in there, and I'm okay with that. I don't mind y'all experiencing it from reading the section, but I'm not covering the section, and it's not going to be on a test. So you're not going to get it on any test questions except for possibly the practice test where I might have missed one, but it's not going to appear on a graded test. All right. If it appears on a test and you like consistently got less than 100 and you want to tell me about it, then let me know and I'll make sure you get 100 for that practice test. It's never come up before, but just in case, I wanted you to know that. And of course, you're always going to answer the chapter opening question. But we're going to start off with the example in the book, which shows a professional tennis player, Roger Federer, I think it is, in example 9-1. So let's look at example 9-1. Example 9-1 says for a top tennis player or for a top player, a tennis ball may leave the racket on the serve with a speed of 55 meters per second, which is about 120 miles per hour. If the ball has a mass of 0.060 kilograms and it's in contact with the racket for about 4 milliseconds, estimate the average force on the ball. Would this force be large enough to lift a 70 kilogram person? So that's what they're asking. That's what the question is. What we know is the mass of the ball is 0.060 kilogram. I'm going to keep the two sig figs. The initial velocity, V initial, is zero. The final velocity, V final, is going to be 55 meters per second. I would say that this is a little dated in that even by the time this textbook was written, which was only in the last couple of years, we had already moved to the point where basically most of the professional women are hitting tennis serves at 120 miles per hour. Uh, so even, we're not just talking to Venus and Serena Williams, who are very, very strong female tennis players. We're talking just about all the tennis players are hitting at 120, and Venus and Serena are hitting at 130. Venus, I don't even think is playing anymore, but Serena just re-entered, and she's hitting 130, even 135 on occasion. And men are hitting around 140, 142, something like that. We've got that. Oh, and we've got delta T is equal to 4.0 milliseconds. So what we want to figure out is what is the average force F bar equals question mark. Solution for this solution, and I know that L turned out really bad, so I can't just let that go. For this solution, what we're going to use is the summation of the forces is equal to dp dt, which means that we could say the average net force, because when you're hitting a tennis ball, all the other forces are nothing. on the tennis ball. There's gravity that's pulling it down, but its mass is 0.060. So even if you multiply it by 9.8, you get up to zero point 0.6 newtons. So what, right? So that's a really small force. The air resistance is small, at least for the split second that it's speeding up. So really, it's the only force. So I'm replacing the sum of the forces with just the average force that the strings of the racket are putting on the ball, and that's going to be equal to the change in momentum over the change in time. It's all along a one-dimensional line because we're imagining it just hitting through the ball parallel to the ground, maybe, or maybe slightly upward. In fact, it has to be slightly upward. You can figure that out if you actually try to calculate how tall someone has to be or how hard someone has to hit the ball to hit it over the net. You can't do that without hitting up on the ball, even though it doesn't look like they're hitting up, but there definitely are. So, with that in mind, I can say F average is equal to delta P and delta P over delta T, and delta P is equal to M V final minus V initial. I could write that as MV final minus MV initial, but it's the same thing. And then over delta T. So this is 0.060 kilograms times the final velocity, which is 55 meters per second minus zero point 0.0 meters per second, divided by 4.0 times 10 to the negative third seconds. And this gives us an average force equal to zero point zero 0.06 times 55 divided by 4 times 10 to the negative 3. That gives me 825 newtons is equal to the average force. And I keep writing a vector symbol over there. That's supposed to be just a bar for representing the average. So that's what our average force is, about 830 newtons. Now it says, how would that compare to lifting a 70 kilogram person? So just for checking, the weight of a 70 kilogram person is M times G, which is equal to 70 kilograms times 9.80 meters per second, and 70 times 9.8 gives me 800 or 686 newtons, which is less than the average force. So, in fact, that force, which by the way, a 70 kilogram person weighs around 150 pounds. So, you can imagine Roger Federer is actually hitting the ball with a force over 150 pounds. Any questions on that? All right, so that's one problem we can work and pretty straightforwardly. The other one is example 9.2, and we still got about 18 minutes, so we're okay with that. So example, darn it. Example 9.2, water leaves a hose at a rate of 1.5 kilograms per second with a speed of 20 meters per second and is aimed at the side of a car, which stops it. That is, we ignore any splashing back. What is the force exerted by the water on the car? So, what we have here is notice we were given a quantity that doesn't sound like anything we've ever run into before, 1.5 kilograms per second. So what I'm going to say is that is delta M over delta T, which you might have called it dm over dt. Either one of those are acceptable, but that's the symbol that I'm giving it, and it's 1.5 kilograms per second. That's how much water in mass is released every second. And in fact, the velocity initially is 20.0 meters per second, and the zero after the decimal is not a sig fig. What we're wanting to calculate is what is the force on the car due to the water, roughly. Solution, I'm going to apply Newton's second law. The summation of the forces is equal to dp dt. But if we talk in terms of averages, we remember in this case, this is sort of like the tennis ball. I'm squirting water out of a hose. It's going to hit a car, and that car is the majority of the force that we're dealing with. So it's way bigger than any other forces. So we're going to replace that summation of the forces with just an average force. So we'll say, therefore, that's what the three dots means. Therefore, the average force is approximately equal to delta P over delta T. Now, delta P is equal to delta MV over delta T, which we might choose to write as delta M over delta T times V. And that's what we're going to do. Now, in reality, what we're calculating is the force on the water due to the car, and therefore it's going to come out with sort of a reverse scenario, if you will, meaning the force on the water due to the car is to the left, whereas the force on the car due to the water is to the right. But Newton's third law says that they're equal in magnitude but opposite in direction. So that's what we're dealing with here. But, anyways, the average force is going to be roughly equal to 1.5 kilograms per second. That's the delta M over delta T times the actual velocity, which is 20.0 meters per second. And of course, if you multiply 20 times 1.5, you end up getting 30. So this is in fact 30 newtons. And that would be, like I said, the force of the car on the water, but the force of the water on the car is the same in magnitude. So we're going to say that the force due to this water hose is in fact about 30 newtons. Any questions on that? So that's pretty straightforward. You could do P final minus P initial. That was the way I did it last night. And in so doing, what I did is I imagined, for instance, that during a single second interval, if you watch it for a whole second, 1.5 kilograms of water is going to come out. So you're imagining 1.5 kilograms of water hitting the car and just spreading out over it instead of bouncing back. Then the final velocity is actually going to be zero and the initial velocity is going to be 20. So you end up getting zero minus 20, which gives us a negative 30 newtons over 1 second. And that was what I was talking about, how the forces would be oppositely applied. But this is a nice way of doing it, sort of quick and dirty. Yeah, do you have a question, Michael?
Yeah, so would it be incorrect to do like a plus or minus 30 or
It wouldn't. It would be if you're trying to answer one question, but you could say positive 30
Mhm.
newtons is the force that the water applied to the car based on my coordinate system, and negative 30 newtons is the force that the car applied to the water based on my coordinate system.
Okay,
Does that make sense?
Mhm.
Yeah, and actually, this way is sort of a quick and dirty way of doing it that I just sort of make up sometimes and use, but it's probably a little more accurate to treat the momentum like I was telling you, like the book does in the solution. But either way, they're all good. So we've done that. What do I do? Oh, yeah, there is a conservation of momentum. So I want to show you what are the ramifications of conservation of momentum. So, conservation of momentum. Darn it. I knew it was going to do that. Conservation of momentum applied. Okay, so you might want to know, what do you mean by conservation of momentum? We've already learned that conservation of momentum means P is a constant, which we can interpret as P initial equals P final. But another way we can think of that is we can say, here's a ball of mass ma traveling with a velocity va towards another ball of mass, oops, of mass mb traveling with velocity VB towards each other. What's going to happen is these two masses are going to run into each other like this, and then that is going to. So you got to make little noises so it sounds like a real thing. And then, of course, they're going to bounce off each other. And what you're going to find then is the blue ball is moving to the left and the purple ball is moving to the right. And now their velocities are a little different. This velocity we're going to call VB prime, and that's the difference between before some event like a collision and after some event like a collision. The velocities go from VA to VA prime and from VB to VB prime. So when we say P equals a constant, that is a vector constant. So specifically what we mean is MAVA vector plus MBVB vector is equal to MAVA prime vector plus MBVB prime vector, which can be broken down into individual components. So you'd have an equation for the x components, MA VA sub x plus MB VB sub x is equal to MA VA prime sub x plus MB VB prime sub x, and then a similar one with the subscripts y. So you actually get two equations out of it. That's the main thing I wanted you to understand in conservation of momentum. There also happens to be something called an elastic collision in elastic collisions. Kinetic energy, oops, energy is conserved. So in that case, you would say 1 half MAVA squared plus 1 half MB VB squared is equal to 1 half MA VA prime squared plus 1 half MB VB prime squared. So that's conservation of kinetic energy, and that only occurs when they tell you the collision is elastic. If you're talking about atomic collisions, collisions between individual particles, if the time interval is so small that the electric attraction or the gravitational attraction, which always the gravitational attraction is going to be too weak, but if the electrical attraction between the individual charged particles is very small or happens for a very small period of time, then virtually all those collisions are elastic. So you can use conservation of kinetic energy there. But that's another thing that we're going to talk about. I just want to do one more example that'll be easy peasy, which is an example of conservation of momentum, and that's example 9.3. So let's do example 9.3, and we'll call it a day. And it looks like this is more or less the same place we got yesterday, so there's really no need to watch that other one, that other video. So railroad cars collide, momentum conserved. A 10,000 kilogram railroad car A traveling at speed of 8.0 meters per second strikes an identical car B at rest. If the cars lock together as a result of the collision, what is their common speed just afterwards? By the way, this collision is called a perfectly inelastic collision, and the reason why is elastic refers to kinetic energy. If you jump to what we call the center of mass frame, which is a little bit of a misnomer. The center of mass frame is the frame in which all the things that are colliding have a total linear momentum of zero. So in this case, we've got a single 10,000 kilogram train car moving to the right at 8 meters per second and another 10,000 kilogram train car sitting perfectly still. That's not the center of mass frame. If I jump to the center of mass frame, what it would be is a frame that's moving to the right at 4 meters per second. compared to this one. So then what you'd see is the train car on the left is 10,000 kilograms moving at 4 meters per second in the positive direction. And then the car on the right is 10,000 kilograms moving to the left at 4 meters per second. So it's a negative, so that you see M times V is 4,000 kilogram meters per second for the left car, and M times V is negative 4,000 kilogram meters per second for the right car, so that the total momentum is zero. After they collide, the momentum's still going to be zero, so they literally stick together and stay still in that frame. So in that frame, in that center of mass frame, all of the kinetic energy was completely destroyed. So that's why they call it completely inelastic. Now you can see why we use that. But in this case, we're just going to use it in the frame that exists. So it's pretty easy. We have M1 equals M2 is equal to just plain M, which is 10,000 kilograms. And then V, let's call this A and B instead of 1 and 2, because we already worked out stuff in terms of A and B. So the velocity of A is equal to 8.0 meters per second. Velocity of B is equal to zero. What we want to know is velocity A slash B prime equals question mark. Because they're stuck together, you could call it VA, or you could call it VB, or you could call it VA slash B, but they're all prime because it's after the collision. So what we have here is this sucker with 10,000 kilograms moving at 8.0 meters per second is going to run into this sucker that's sitting perfectly still, 10,000 kilograms, V equals zero, and then they're going to collide and stick together and move at a velocity VA slash B prime equals question mark. But the mass here is 20,000 kilograms. So P initial is equal to 10,000 kilograms times 8.0 meters per second, which equals 80,000 kilograms meters per second, which is the units of momentum. I didn't mention that, so wanted to do it now. P final is going to be 20,000 kilograms times V A slash B prime, and that part we don't know. So P initial equals P final, which is conservation of momentum. Therefore, it gives us that 80,000 kilograms meters per second is equal to 20,000 kilograms times VA slash B prime, and therefore VAB prime is equal to 80,000 kilogram meters per second divided by 20,000 kilograms, which gives us 4.0 meters per second. And notice it's in the same direction as the original train car was going. Okay, so that's a typical conservation of momentum problem, a fairly simple one, of course. We'll do a lot more later. We're going to do that. We're going to do center of mass. We're going to have to calculate center of mass using some calculus. So stuff's starting to get hairy now. We'll cover that next time. But you're free to go. Don't forget to get your test done over the break. Have a great July 4th. Feel free to do the test even earlier if you want to. It's already available and you get multiple attempts. So good luck with that, and I'll wait in case you have any questions. But other than that, you're free to go.
Cool. Sounds good. Have a great weekend.
All right, you too, Michael. Have a good one. All right. Oh, cool. Yeah, that's some serious running there. Michael was saying that we used to run the Manitou incline out in Colorado, a massive staircase going up a mountain. That sounds rough. I think I'm having a heart attack just thinking about it. All right, see you, folks. Bye bye.